Welcome everybody.
My dear Dr. Sattler, welcome to Jurassic Park.
This series relates to heat transfer for engineering. This video will give you a brief introduction regarding the mechanism for heat transfer, and the book that I'll be using is The Pitson System for Theory and Problems for Heat Transfer. So after the brief introduction to the mechanisms, we'll do a lot of examples to concrete the same material throughout. So let's get started with heat transfer.
I don't like where this is going.
So generally, for heat transfer, or the movement of heat, if you want to call it that way, it requires a change in T, meaning it requires a temperature gradient. Temperature gradient. Just like in your earlier fluid dynamics class, fluid dynamics, it requires change in pressure to move through. It's the same idea that it requires temperature gradient to move the heat through. Hence, the class is called heat transfer.
You what?
So, the mechanism of heat transfer. There are three main mechanisms: conduction, convection, and radiation. From this picture, it's pretty clear. If we see, conduction generally happens through a solid object, right? So let's put it that here. This convection is happening through fluid movement. Fluid movement. I mean, this could be liquid or gas. I'll give you a more concrete definition in next slides. And radiation happens through electromagnetic waves. So these are the three main mechanisms for heat transfer.
Hold up. Wait a minute. Something ain't right.
Now, let's get started with conduction. I mean, as we said before, conduction relates to what? It relates to solid, right? And for a more concrete definition, you can think of, we need a temperature gradient and a solid material. So if we want to define it properly, we can say a temperature gradient within a homogeneous substance. So basically what this is saying, you need to have a solid and there needs to be a variation of temperature for the heat to move through. Some of them are better conductors, some of them are bad. And as you can recall, for solid, first thing for me, conduction, when I read it, the first thing that comes to mind is copper wire, conductance, electrons. So for basically metals, you move through electrons, and for insulators, you go through phonons, generally through vibrations, let's say that. And this is pretty much it for your definitions. For the conduction, so let's just get into the formula that you need to use for this is, we'll say, Fourier's law. Fourier's law. Now, what is Fourier's law? So it says that Q equals negative K A dt over dx. Now, what is all of this? Let's break down each component in the formula. So Q, let's go by one, dt over dx. For a linear temperature difference, you can basically think of this change in T over change in X. T2 minus T1 over X2 minus X1. Units, K over M. Kelvin over meters. Area, as you all know, it's in meter square, and I don't know what else to say. I mean, it's just the area. And this K is the new term that you guys might not know.
Really?
and this is called thermal. I'll use the new slide. I'll rewrite the formula here. Q equals negative Ka dt over dx. Now K is thermal conductivity. Basically, it's a constant for various materials, and it depends on various other properties such as temperature, pressure, and others. So, what are the units for K? Interesting question. First of all, for Q, it's in watts. Q is watts. So if we were to get the units for K, we know that area is in meter square, and we know that dt over dx is in Kelvin per meter. So everything needs to cancel out to get us Q, watts. So Q, we'll do simple unit analysis over here. Q is in watts equals, we don't know what this is, we know what meter square is, and we know this is K over M. So this goes away with this. So we need to get watts in here, right? So watts need to be up there, and we need to cancel out this meter and this K. So if I was to cancel them out, this goes away and this goes away. So therefore our K equals watts per meter K.
Oh my God!
So for recap, this is what we have. We have this Fourier's law saying this: negative Ka dt over dx. Basically, if I draw this slab right here like this, cool. Let's say this is our x1 and this is our x2, this is our t1, and this is our t2. This negative sign right here comes from second law of thermo that states that heat flows from warm to cold, if you want to put it that way, like high to low temps. K, we said, is thermal conductivity. With units of K watts over meters. Area is in meters squared. dt over dx is the temperature gradient, which in linear profile is this. So all of this is basically your recap for conductance. And just remember that it's in, if you want to put it that way, that it needs to have change in temperature and in solids. That's it. Now let's go to the next one, convection. As we said before, convection relates to what? It relates to, like, fluid flow. So like water and like air, if you want to. I'll try to draw air, and this is little sun coming out of it.
Wow!
So water, some sort of fluid, and air. So we got this. So this is what convection relates to, and if you want to put it in a solid definition, this is the solid definition. So if it's a solid body and it gets introduced to a moving, this is the main word, moving fluid, that has a different, what would be different? Think. Yep, temperature. Always need a gradient temperature for heat to flow through. Remember, that's one thing. Always needs a temperature different for heat to flow through.
Every
then the energy would be convected, and that would lead to convection. And the formula that relates to this is called Newton's law of cooling. Newton's law of cooling. Newton's law of cooling states Q equals H A T S minus D infinity. Now
I got scared. I dropped my hot pocket.
let's go through each of them. So Q equals, as we said in the previous one, it's watts, right? So let's say this. We don't know what H is, so let's leave it right now. We know what area is.
No shit, Sherlock.
It's in meter square. TS relates to temperature of solid at surface. And T infinity is the temperature of fluid. Whether it's air or water, whatever's moving around that solid, it's that temperature. So infinity, think of like a overall, like outside.
Infinity and beyond.
So what is H? H, a lot of you might not know. H relates to, it's so just like we had thermal conductivity for conduction, H is a convecting heat transfer coefficient. So if I write that down, it's convective heat transfer coefficient, and the units for H are this. It's not the same thing, first of all. Meter square times K, or it's BTU per hour times feet square degrees F. These are the units for H. Cool. So to recap everything, the whole idea of the formula, we got Q equals H A T S minus T infinity. Q is the heat in watts. H is the convective heat transfer coefficients in watts per meter square K. And area is in meters squared. And this is the temperature difference between the solid surface and the fluid that's moving through. Moving fluid. Yeah, so that is all for convection. Let's move to the next one, radiation. Radiation relates to what? Radiation, when I think of it electromagnetic. So radiation relates to electromagnetic wave propagation. So the formula for radiation is Q equals sigma A T to the 4 times E.
And then the smoke got me. I got bronchitis. Ain't nobody got time for that.
So Q in this case is heat. Same thing like we had before, and it's in watts. E is emissivity. Emissivity of the surface, and it's unitless, but it goes from 0 to 1. Just know that a black body, this one relates to a black body, right? Sigma is your Stefan Boltzmann constant. Stefan Boltz, let's write that, constant, and it is 5.6697 times 10 to the negative 9. I lied, it's 8. 10 to the negative 8 watts per meter square times K to the fourth. and area is in meter square, and temp, it's the absolute, this is the important part, it's the absolute temperature, therefore it's in Kelvin or Rankins. Alright, let's connect all the radiation part, conduction part, and convection part together. So conduction, we know that it happens through solid and we need a temperature gradient, right? And it's represented by Fourier's law, where it's Q equals negative Ka dt over dx. We know that K is our thermal conductivity with a unit of watts per meter K. A is area, dt over dx is change in T over change in X. And for all of these, remember this, basically, that Q is given in watts, right? Next is, let's do convection. Remember, water, air, so it happens through fluid, right? When fluid moves through a solid body, and at the same time, there needs to be a temperature between the fluid that's moving through over the solid body. Only then the heat transfer can happen. And this is represented by Newton's law of cooling, where this is this, HA ds minus T infinity. And we said that T infinity is for the fluids. TS is basically surface of the fluid, or surface of the solids actually. A is area, and H is the convective heat transfer coefficient, which has a units of watts per meter squared K, or BTU per hour times feet square degrees F. And next is radiation. Radiation is very simple actually. We know that this happened through electromagnetic propagations of waves, and it is given by Q equal E sigma A T to the fourth. E is your emissivity. Emissivity is E. Sigma is that Stefan constant. I'll write it 5.667 times 10 to the negative 8. You can write up the units from the previous slide here. A is our area, and T is our temperature. Remember, absolute temperature. That's the main function.
I've never felt power like this before.
To go through some of the general knowledge or some of the properties that, I mean, you know them, but still a good way to go through them. I'll just write down the definition, but you know them pretty well. So let's go through. Density is one, which is basically what? Mass over volume, which is kilograms per meter cubed, as in its units. Next is, let's go, specific volume. Specific volume, which is basically 1 over density. Actually, this is this specific volume, which is this, equals 1 over density. So basically the units are flipped, so it's meters cubed per kilogram. Next is specific gravity. This is actually important. So sometimes in the question, specific gravity is given. So like you have to find your own density. So specific gravity is density over density of water. And this equals specific gravity. So if I give you specific gravity of 1, this is saying for some metal, whatever, divide by density of water. So density of metal is basically density of water times 1. equals density of metal. So 1000 kilogram per meter cube times 1 equal density of the metal. So this is one way specific gravity is actually very helpful to find. And one more term that's really important is thermal diffusivity. And it's just a definition, just keep in mind K over density times Cp. I mean, we know what K is, right? It's from the conduction part, which is this right here. So thermal conductivity divided by this right here is thermal capacity. This is the definition, just keep that in mind. And the units for this is meter squared per second. So just like almost meters per second square, but instead it's meters squared per second. Also, important part, no viscosity, especially difference between dynamic versus kinematic. This is also one good way, because sometimes you're given both the dynamic and kinematic viscosity and you need to find out temperature. So kinematic viscosity equals dynamic viscosity divided by density. And the units for this are same as thermal diffusivity, which is meter squared per second or feet squared per second. Cool. And the units for dynamic viscosity are kilograms per meter times seconds. That's it. So density, mass over volume, kilograms per meter cube, specific volume, which is 1 over density, specific gravity, which is density over density of water, thermal diffusivity, which is K over density times Cp, which is basically thermal conductivity divided by thermal capacity, and know the difference between dynamic and kinematic viscosity. And remember that the units are the same for kinematic and thermal diffusivity. You know, something that way you can recall and connect the dots together.
It's done.
Let's jump to some problems. So determine the steady state rate for heat transfer per unit area through a 4.0 centimeter thick homogeneous slab. Homogeneous slab, right? As soon as I read this word, this triggers conduction, right? With its two faces maintained at uniform temperature of, let's make this 38 C, and this is 21 C. Okay, the thermal conductivity is 0.19 watts per meter K. Let's write down what we have and what we need. Okay, so we have the thickness to be given to 4.0 centimeter. Let's convert that to meters, everything. So 100 centimeter are in 1 meter. Put that. We have T1 to be 38 and we have T2 to be 21, right? And changing X is, this T is basically changing X. This is 4.0 times 10 to the negative 2 meters. So let's find out, and yeah, K is also given, 0.19 watts per meter K. Eventually what you need to find out is Q over area. And what's the definition for conduction? Conduction Q is negative K times A dt over dx, right? So if you need to find Q over A, divide by A, so you got Q over A equals negative K times dt over dx. Now overall, plugging everything in is you get Q over A equals negative 0.19 times T2 is 21 minus 38 over change in X of 4.0 times 10 to the negative 2. So I will plug everything in my calculator and then
Derpity derp 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 derpity derp 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 derpity derp 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 derpity derp 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 derp.
I got positive 80.75, and remember it's heat per area, so it's watts per meter squared. This is, just keep in mind what you're trying to find and what type of formula you want to relate it to. I actually want to show that this actually, I'll show it on this page, but how this relates to that linear composition of, so check this out. So let's say you have this slab, right? We know that the change in X is 4.0 times 10 to the negative 2 meters. But T1 is higher and T2 is lower. Why? Because we know that from that negative sign, heat flows from warm to cold. Just remember that. Just think about it. And then let this idea sink in. Why is there's a negative sign? Alright. So that's done. Let's do this one. The forced convective heat transfer coefficient for the hot fluid over a cool surface is this. Okay, so we know that our H is 225 watts per meter squared C. For a particular problem, the fluid temperature upstream, okay, the T fluid is 10 degrees C and the surface is held at 1, T surface is 120 C. Determine the heat transfer rate per area. Remember, what does it say? Surface area. So in your convective formula, when it's this, honestly, you can put a little s in there, so this reminds you that it's a surface area. Cool? Like this represents the surface temperature, so this would represent surface area. So you need to find Q over AS, which is H times TS minus T infinity. So our H is what? H is given to 225. 225 watts per meter square C. TS is 120. 120 C minus 10 C. And when you put all of that in the calculator, you get approximately 24,750 watts per meter squared. This is Q over area, surface area. Remember, for convective, it's surface area. Let's do this problem on radiation. So after sunset, radiant energy can be separated by a person standing near a brick wall. Such walls frequently have surface temperature around 44 C. And typical brick emissivity value is 0.92. What would be the radiant thermal flux per square area? So we need to find this. The radiation formula is this, E sigma A, T to the fourth. We need to get Q over A to be E sigma T to the fourth. Don't confuse the sigma with surface tension, which would come later, but this is Stefan constant. Cool. So I get Q over A equals 0.92 times 5.667 times 10 to the negative 8 watts per meter squared to the k to the fourth. Multiply that by temperature, which is 44 degrees C.
It was at this
Right.
moment he knew.
No, this is wrong basically. This should be absolute temperature, right? So this would be 273.15 K. So you need to, whenever you do the radiation, make sure you're taking the absolute temperature into account. 317.15 to the fourth. So if I do this, plug everything in my calculator, 6697 times 10 to the negative 8.92, you get approximately 527 watts per meter squared. Keep in mind, for radiation, you need absolute temperature. Alright. In summer, parked mobile surfaces frequently average from 40 to 50 degrees C. Assuming 45 C as the surface temperature and emissivity of 0.9, determine the radiant thermal flux for the car roof. So this is the same idea. It's the same problem. Q over A equal E sigma T to the fourth. And we know emissivity is 0.9. Stefan constant 5.6697 times 10 to the negative 8 watts per meter square. K to the fourth. This is surface temperature, which is 45 plus 273.15. Put everything together to the fourth, and you get Q over A equals 522 watts per meter squared. That's all for radiation. Let's verify some of these unit conversions. This is really important. I would say memorize these conversion factors. So these would be really helpful to convert from English units to most of the metric units, and these are really important. So let's convert 1 BTU per feet squared times H. If I multiply that by 1054.35 joules in 1 BTU, I need to convert hours to seconds. So 1 hour has 3600 seconds. And then I also need to convert feet squared to meter squared. So 3.28 feet squared is 1 meter squared. So if I put everything back in, I should get this value right here. So let's try putting everything back in. And I would encourage you to put everything back into your calculator, so this would be some good practice. So you get 3.15. Let's try another one. 1 BTU per hour. We know that 1 BTU has 1054.35 joules, and 1 hour has 3600 seconds. So if I put everything back in together, I get 0.292875 watts. Important just to convert straight from BTU to watts. And 1 BTU per hour times feet squared, you won't take it squared, times this. Whenever I do the whole thing, I get 1054.35 joules in 1 BTU. Multiply that by 3.28 feet in 1 meter. Multiply that by 1 hour has 3600 seconds and multiply by 9 degree Fahrenheit to 5 K, and you get 1.72958 watts per meter K. An easy way to convert the units of K, the thermal conductivity, in conductance, right? So keep in mind, these are good conversion factors, and I would encourage you to memorize these. Next problem. This is a long problem, so I would encourage you to pause the video and just read it through and just write everything down of whatever you know, but I'm gonna do it anyways. The air inside an electronics package housing has a temperature of 50 degrees Celsius. So the T inside is 50. The air, so air that's moving has a T of 50 degrees C. Cool. A chip in the housing has an internal thermal generation at a rate of this. So in this case, we're given Q, which is 3 times 10 to the negative 3 watts. The chip is subjected to an airflow. Airflow, therefore we have convective, right? Airflow, air, fluids flow, yeah. H equals 9 watts per meter squared C. Over its two main surface area, which are 0.5 to 1.0 centimeter. So if I was to draw this whole thing out, let's say it looks like this. Cool. And you got a length of 1.0 centimeter, and this is 0.5 centimeters. And this is happening from two main surfaces, right? And we know that convective is this: Q equals H A Ts minus T infinity. We need to find out Ts is. Okay. In this case, we need to find out first area, which is the really important part. Other than that, everything is given. So area is the surface area. So you would take 0.5 times 1.0, right? That's one area, but it's going to two main surfaces, so you just multiply it by 2. But you need to, I would recommend convert everything in the meter squared or meters, so you don't have to worry about it later. So 2, which is two main surfaces, times 0.5 centimeter divided by 100 centimeters to convert them to meters, multiply that by 1.0 centimeter divided by 100 centimeters. Plug everything in that calculator, you get 10 to the negative 4 meters squared. So now to calculate for HS, you know Q is 3 times 10 to the negative 3. You divide it by area, which is 10 to the negative 4. I will rewrite this. 3 times 10 to the negative 3. Divide that by area, which is 10 to the negative 4. Divided that by H, which is 9. And then all of this added the ambient temperature of air. Air is flowing like this at Ts of 50, T infinity of 50 plus 50C, and you get 53.33. What does this number signify? It signifies that heat flows from higher temperature to lower temperature, therefore convective to air. Because air is at a lower temperature. That's all for this convective problem. Let's go to this one. A plane wall. Let's draw this. I'm gonna give you like the first one. I'm gonna draw this for conduction. It's really actually a good idea for you to draw this. So T2 is right here, T1, and this is change in X. Okay, 70, T1 is 20, K is 0.40 watts per meter K, and thickness is 0.15 times 10 to the negative 2 meters. Imagine I converted centimeters straight to meters down there. Now you need to find out area, like Q over A, which is same as negative K times change in T over change in X. K is given to be 0.40 negative times T2, which is 70 minus 20. Divide that by change in X of this, and this total equals negative 133 watts per meter squared. So negative flow opposite. Alright. Forced air flows over convective region. Heat transfer H. It's given to be 200 BTU per H feet squared degrees Fahrenheit. The surface temperature is considered constant at 150 F. The air is ambient at 65 F. Determine the heat exchanger surface area required for 30,000 BTU per hour of heating. So you're trying to find area in this case, and Q is given. Q equals H A Ts minus T infinity. 30,000 BTU per H, divide this whole thing by 200 BTU per H times feet squared degrees Fahrenheit, and divide by 150 minus 65, and you get, let's put everything back in calculator. 50 minus 65 squared. Now 30,000. Divide that by that number. 1 point, had some calculator issues there. 765 feet squared. And that's your area. And I think this is the last problem that I have for this video. Exhibit temperatures of approximately 50 C. So T surface is 50 C. Consider surface image as a black body. So we know that black body has an emissivity of 1. Calculate radiate per unit of surface area. We still need to find Q over A. So Q equals emissivity sigma A T to the 4th. Now Q over A equals E sigma T to the 4th. And what did we say for this temperature? It's absolute. Thereby, this is 273.15. Right, so we know that E is 1, Stefan constant 5.6697 times 10 to the negative 8. I'm not going to write the units down because we know everything is converted to the right units. So everything works out. I've showed you that before. So now put everything back in. 4th. Multiply that by 5. You get approximately 617 watts per meter squared, and this is 323.15 to the 4th.